is de facto method of choice for many applications, for many domains where the data is tabular, right? So where we don't have any perception tasks, but we rather have some clear attributes and we want to classify based on them. So we don't need to extract any features, right? So we can just work directly with tabular data. And this kind of classifiers, such as XGBoost and so on, right, which belongs to this family, they are very popular on data science competitions like Kaggle and so on. But at the time when we were doing this work, there have been only a few papers that focused on the robustness aspect of them. So we kind of contributed a bit more, and we showed how to do probably robust training of this family of models, which has its own challenges because one problem is that these classifiers are discrete. So kind of the function, so you cannot optimize, you can find adversarial examples using gradient descent. So yeah, so this poses some new challenges, and we propose a method how to essentially work around them. So yeah, and I'm happy to answer any questions.
Thank you, Maxime. Indeed, I found your work really interesting. I merged two questions. One is from me and the other one is for Mark, but they were really similar. Mm-hmm. So I will read more questions. Is there a generally accepted approach on how to scale and distribute attacker budget on heterogeneous tabular data?
Yeah, that's a great question. So yeah, so kind of the threat model that we considered in our paper was L-infinity perturbations, which can be easily generalized to arbitrary box constraints, right? Which means that for every feature you have some range of values that you want to be robust at, right? But it's a good question. So, and it's kind of a question to domain experts how to set this range. And it's something that we don't have, we didn't have a good answer in our paper, right? So kind of, we just assumed that, okay, that we have some epsilon, some fixed budget for every feature, and then we want to be robust against that. But clearly it's just a proof of concept. And in order to make it really meaningful, I think one would need to really talk to particular domain experts and define this bound based on particular data and also particular goals that are pursued, right? So I think that's how it should be done.
Okay, Jayant, do we have a little bit more time?
Yes, for one question, yes.
Okay, so maybe one question about your experiments. Mm-hmm. I was wondering, when you say we had performed almost all provable defenses for CNNs, I was wondering what kind of experiments exactly you run.
Okay, so basically we compared an ensemble of boosted decision trees trained on 3 different data sets. It was MNIST, it was German traffic sign data set, and it was I think Cypher10. And we compared to the existing approaches which were reported in the literature, and it came out that the results that we obtained using boosted trees are in fact very close to the state of the art. So we just used some popular L-infinity thresholds, like the sizes of L-infinity radius, like 0.3 on MNIST or stuff like this, right? And we were actually quite surprised by this finding that that this kind of very simple classifier, which is just based on on this thresholds, like that if the value of some combination of pixels is greater than some value, right, then we predict this, otherwise we predict that. So it's kind of very simple classifier, which is not really suitable for computer vision, but nonetheless we could achieve quite competitive results in terms of probable robustness.
Okay, thank you, Maxime.
I've shown 2 recent works from our group where we go beyond the standard LP ball setting, but we actually use LP robustness in what we do. So first, we build on randomized smoothing. So randomized smoothing is an interesting technique since it provides a sound guarantee if you can approximate an integral, or if you can solve an integral. But in practice, we can't really solve that, so we need to approximate that integral, and then there's results from statistics telling us, okay, we can solve it with a confidence arbitrarily close to 1, but so this is probabilistic certification, so this is in an interesting space between formal and empirical verification. so to say. Yeah, but due to this trade-off, it scales to much larger models and data sets than what we currently do with standard formal methods. So this scales to ImageNet certification, for example. And in our work, we extend this to parametric transformations. So for example, image rotations, image translations. And what is challenging there is to incorporate the interpolation error actually caused by these operations in the computer, since we represent images on a pixel grid. So if you rotate it by 5 degrees, then we still need to align it with the pixel grid, and there we get a large error. And in our work, we actually combine formal methods with this randomized smoothing approach to deal with this interpolation noise. And in the second work, we show how we can achieve provable individual fairness. So here we build on the on standard formal verification. So we use over-approximation, and we use mixed integer linear programming. And we show that similar individuals get treated similarly. So if we're in the setting of whether to approve a credit for a person or not, we see this as a classification problem, and we ensure that similar individuals get classified the same. So either get the credit or not. And what is a similar individual is specified by logical formula. Yeah.
Okay. Thank you, Mark. So I have one question for you. Let me check here. So the question is from Juan. I think you've got a lot of discussion. You should have, because you're working on similar topics. So the question is, when you learn a fair representation, how do you guarantee that the data producer, which is a neural network, can accurately encode the similarity function? So is it possible to guarantee that the producer correctly produces a set of the representation of all similar individuals for all possible inputs, including those not included in training datasets?
The short answer, no. The more interesting answer is, this is essentially the same as if we are training a neural network to be robust or to be amendable to formal verification. Then in all these cases, we train it, and for the single training example, we usually know whether we can verify it, or in an empirical setting whether we are robust. But we can't fully extrapolate this to unseen data. So what we do is we train the model so that this property hopefully holds on as much training data as possible with the standard empirical risk minimization setting. And then at inference, so then at test time, we show that this holds for, let's say, 80–90% of the data set. And then if our new unseen data follows the same data distribution as the test set, we can expect it to hold on these. However, what we can also do in practice, if we do inference, we can also run the verification at inference, since in the fairness setting we have tabular data that is relatively small. It's not that costly to run the verification, even though it uses mixed integer linear programming, but it's still manageable to run it at inference time and get the proof.
Thank you, Mark.
Thank you. So in the paper that I presented, we studied the topic of abstraction. So we want to verify a neural network, and today there are many tools that will do this for you, but all of them are struggling with network sizes. So the larger the network, the exponentially more difficult it is to verify. So what we wanted to do was take the neural network and replace it with a smaller version that was easier to verify. So this is the very widespread notion of abstraction. So the method that we proposed for doing this was by merging neurons. So we do a certain pre-processing on the neural network and bring it to a situation where you can merge neurons together. So every time you merge, the neural network size is decreased by 1. And you can merge and merge and merge again and again and get a very, very small neural network. And we show how you can do this in a sound way. So if the smaller neural network that you get turns out to be safe, then so is the original. If the smaller neural network turns out to be unsafe, then you may need to do a refinement step, which is, again, a very common thing in verification. And so the nice thing about this technique is that it's orthogonal to the verification engine that you use. Right? You can make your neural network smaller, and then you can verify it with whatever technology that you want to. So I think that's my 1-minute overview. If you have any questions, I'll be happy to.
Okay, I have many questions, but I needed to pick some. For those who are not, who are still eager to have an answer, do not hesitate to chat in the coffee room after. So the two selected questions, one is from Katerina. So she's asking, any idea on how to generalize your abstraction to other neural networks with other activation functions, for example?
So I think for all activation functions that are piecewise linear, for example, max pooling, average pooling, leaky ReLUs, all of those you can express one in terms of the other. So once you have a technique for ReLUs, you can take many of these other piecewise linear activation functions, express them as ReLUs, and then do the technique. For activation functions that are not piecewise linear, this is something that many verification engines are struggling with. So I think one approach that we haven't done yet, but we are thinking about, is to first approximate. Say you have a sigmoid function, you can approximate it using a piecewise linear function, and then abstract that approximation.
Okay. Thank you. And the second question, yes, it's from Mark. So Mark Mueller is asking, can this approach be extended to more complex architectures such as Resnets or DenseNets? It seems like the minimum number of condensed numbers would be exponential in the number of direct child layers.
So the approach that we propose can be applied to any network that is feed-forward. Right? So for example, as long as you don't have a recurrent network or something like that, that should be fine. It doesn't matter if it's sparse or dense or convolutional, that's fine. And the maximal increase in size that you might get is by a factor of 4. Right? So there's no exponential increase. If your network has, say, 100 nodes, then in the worst case, you will have 400 nodes because of our preprocessing. But the blow-up will not be exponential.
Okay, so we are done. Thank you, Guy. We are done with your question.
I'll try to play these videos to give you a better understanding. So in the presentation, the motivation of our work is to ensure that the formal method can actually help us solve the real-world applications, like how to ensure those safety critical applications that the robot policy is well verified. And we do that. So in the presentation, we discussed two approaches. One is that built on top of our neural verification toolbox. We want to compose different algorithms together to scale them up to real-world problems. And second is that in a lot of real-world applications, we will need to adapt our neural networks in real time in order to make it fit the current situation. And once the parameters of the network changes, we need to do quick re-verification to make sure it still satisfies the specification. And then we did a lot of exploration to enable this kind of runtime sound verification of neural networks. So yeah, that's the idea.
Perfect. 1 minute, perfect. So I have two questions for you, Changyu. The first one is from Mark. So I'm reading it. Could you expand on what is considered an unaffected branch in the adaptation setting? Have you experimented with applying special additional regularization to the updates to increase the portion of unaffected branches?
Yeah, so unaffected branches are those essentially in the current research, we use symbolic propagation, and together with search, which is a method very similar to ReLUval or Neurify. And the unaffected branches, those that the change of the network parameter did not affect the resulting symbolic reachable set at the output layer. If we find these symbolic set are not affected, we just directly concretize that symbolic set without doing the forward propagation again to save some computation power. And this is a kind of early work. We haven't tried to combine with other approaches to make this process easier and to expand the possibility of those reachable set being unchanged. But that is what we try to do in the future.
Good luck with that. We will all be interested. My second question, it's from me actually. I was more curious about your Julia library, neural verification, which I had the occasion to use before the workshop actually. I was wondering if you compared your re-implementation of AI Cube or all the other methods with the code provided by the authors, and if you encountered some mismatch between your implementation and their code.
Yes, That's a very good question. So we did do the comparison, and we briefly mentioned in our survey paper that we did observe some huge difference. In some cases, our method performs almost the same. In some rare cases, we can outperform them, but in most cases, we didn't. And the reason is because when we start to implement this neuralification toolbox, our goal is to provide a pedagogical demonstration. So we didn't do a lot of code-wise optimization. And also our underlying optimized solver may not be as powerful as what has been used in the original implementation. Yeah, but that's definitely one thing we want to address in the future, because if we want to compose different algorithms together and develop new solvers on top of neuralification, we definitely need it to be very efficient.
Okay. Well, that's not an easy task for sure. Maybe I would just add, any plans to add things compatible with Marabou or Eran in the future?
Yes. Maybe not directly compatible adding an interface to Marabou and the related stuff. We will gradually absorb those implementations, those techniques demonstrated working in other solvers, and implement it in the Julia library.
Okay, thank you.
Hello, I hope you can see my desktop being shared now.
Yes,
so I also am going to present two bugs. So I did present two bugs. The first one is on ACE, which are compositional architectures for easier robustness certification. And essentially the idea is based on having two networks, one shallow certifiable network and one deep state-of-the-art not certifiable network, and then one decision mechanism deciding on a per sample basis during inference time which network to use. And this effectively allows us to do a much more efficient trade-off of natural and certifiable accuracy. Here in yellow, you see reference curves of state-of-the-art models tuned to different trade-off settings, and the squares are results that we get with ACE, which is generally, or we assume, would be interesting for applications where natural accuracy is still very important. Then the second setting is in incomplete certification based on the propagation of abstract elements. And there, for most methods, affine layers are no problem, but encoding the nonlinearities is the main challenge here. And most methods or most transformers that are used there suffer from the so-called convex barrier that's illustrated here. So to propagate a convex shape through the network, you have to use some convex approximation of the individual activation functions, which was long thought to be the limit of this approach. But it has been shown that there are convex barrier breaking methods. So far, they were very slow. And with Prima, we introduced a method that's about 2 to 3 orders of magnitude faster. And effectively, here we approximate groups of neurons jointly. And the very high level idea is that we take the input space on of the neurons that we approximate together, split this into regions where we have exact or at least tight linear bounds on the activation function. There expand the corresponding polyhedra, apply those bounds, and then compute the convex hull over these quadrants or these polyhedra, and the constraints that define the resulting convex hull of these hyperplanes are then added to an LP problem, which is solved for the certification. And this compares favorably both in terms of precision or accuracy and runtime to other precise incomplete methods that are available at the moment. And now I'm very happy to take any questions.
Great, thank you, Mark, and congratulations for your results. I have two questions. One is from Juan. So Juan is asking, in your talk, you successfully break the single neuron convex relaxation barriers by relaxing a group of neurons in a convex hull. So how does the complexity of the algorithm grows with K, the number of neurons in a group? In the extreme case, suppose we can form a convex hull for all neurons. How large the relaxation barrier will be, and compared to complete verifiers such as MIP?
Okay, so first of all, the convex hull or approximate convex hull algorithm that we implemented scales quartically with the number of input constraints, but we use an approximate projection method to project the input polyhedra onto the groups, so onto which then effectively results in an exponential dependency of these input constraints on the number of neurons. So scaling to the full layer is not feasible. Actually, with our approach, we can scale to group sizes of about 5, although those are already quite slow. And with other implementations or with a similar approach, you can not scale beyond k = 3, and even that is only possible there for piecewise linear activation functions. With regards to how this compares, or how this would compare with a MILP certification, this is difficult to say, as this won't be feasible at all. We gain up to a factor 20, 30 in output volume compared to single neuron convex barrier relaxations.
Okay, thank you, Mark. Your second question is from David Stutz. So in your AC paper, you use an additional network to decide whether to use a probably robust network or a standard network. How exactly is this network trained, and how did you evaluate robustness? And second question, does the attacker know of this additional network and is taken into account for the attack?
Okay, maybe I'll answer the second question first. So this is taken into account. The robustness numbers or the robust accuracy that we give are proven for the whole network. So there, the knowledge of the attacker doesn't matter, as these are actual proofs. We also evaluated adaptive attacks, and the adversarial robustness numbers or the empirical robustness numbers that we report in our paper use an overly pessimistic adaptive attack, where we actually attack all the components of the network separately and then combine worst cases to ensure that there's no gradient masking or no such effect leading to better results than they actually are. And with regards to the first question, we use the same verification techniques for the selection network that we use for the certifiable network. In this case, this was these were various methods from Crown IBP and Cold, so which is then the Deep Z certification, and also simply IBP, which were also used for training there.
Okay, I think we will stop now because we are running out of time, but really thank you, Mark. It was really interesting.
So we introduce a methodology for the assurance of machine learning for the use in autonomous system that we call it AMLAS. And the aim of this methodology is to integrate safety assurance into the development of machine learning components. So this means doing assurance while we are developing the components itself, and also generating the evidence that is at the base of the safety case that then will be used to assure that the component is safe when deployed in a complex system. The idea is that in this way we can use the machine learning component in safety critical application, and we can gain the benefits of this technology also where we need to ensure enough confidence in the safety of this system itself. So the methodology itself comprises a process and a series of safety patterns that we can instantiate to have as a result the safety case for the machine learning component integrated in the complex system. Yes, that's all I think. And yeah, I'm happy to reply to any question.
Thank you, Chiara, and the perfect time. So I have several questions for you, but I have picked two of it. So the first one is from Giant. So Giant is wondering, do you have examples for data requirements? In the case of images, how do you specify the data requirements?
Okay, for the data requirements, we need to take in account about relevance, completeness, accuracy, and balance. Relevancy is how the data are relevant to our domain. And I can give an example of this. For example, if we are talking about an object detection, we need to be sure that the image that we are given to the machine learning component is orientated in a way that takes in account the position of the sensor. For example, not too high, not too low. So we have the same perception of the sensor in the deployed on the vehicle. So this can be one data requirement. Another data requirements can be completeness, because we need to ensure that the data must be complete in a set of dimension on our operational domain. So, for example, if we know that our vehicle is employed in all time of the day in several weather conditions, we need to take into account in the image. We need to ensure we have a development data, including all the lighting conditions possible in our operational domain. So this can be all the data requirement. But in general, the data requirements is not on the image, is on the set of the data that we have.
Okay,
that's very well.
It's really fine, and if Giant wants to hear more, Giant, you can contact Chiara at the coffee room. We will go on the second question before we are running out of time. So Mark is asking, did I understand correctly? You suggested that the validation dataset should include or even consist only of edge cases or specifically hard samples. If so, how do we define that? What these are, and should we consider this evaluation on out of distribution samples?
Okay, what we call verification dataset. We suggest is done for edge case data that are known to be difficult in our operational domain, like, for example, occlusion in the case of pedestrian detection. But of course, yes, this can be an analysis and evaluation of out of distribution at the same time. Of course, we are aware that it is impossible to characterize all the out of distribution in a complex world. So this is only the case that in a traditional software, considering the edge testing case. Yes, but what we can think, of course. Yeah.
Okay, thank you, Chiara.
Okay, so well, in the work that I presented, what we did was developing a static analysis for proving fairness of neural networks used for classification of tabular data. So the notion of fairness that we considered is a variant, it's some special kind of global robustness property. So essentially, we want that the classification given by the neural network doesn't use the features that are considered sensitive by the user of the analysis or by the user of the neural network and so on. So what we do is an analysis that works in two phases. There is a first phase that is a forward analysis starting from the inputs of the neural network, in which we sort of iteratively partition the input space and we find this activation pattern. So in the paper, we focus mostly, we essentially focus on networks that have a ReLU activation functions. There is then a small paragraph on how to extend it to other activations. But yeah, so for ReLUs, we find these activation patterns for the various partitions of the input space. And so we group partitions together depending on the activation pattern. And then there is a backward analysis that uses these activation patterns to figure out if there are partitions in which inputs that have a certain value of the sensitive feature lead to a different classification
compared to other inputs that have a different value of the sensitive feature. That's all.
Perfect. Thank you, Katrina. So the two questions, one is from Catherine. So she is asking, would it be possible to apply your method by downscaling the models, for example, using a method similar to what Guy Katz proposed?
Yeah, absolutely. So that's in fact something that we are looking into maybe doing right now. The only thing is, so in the paper, the technique that we presented with the domains that we used turns out to also be in practice complete. If we then do an approximation like reducing the size of the neural network, it will become it will lose completeness. It will just be small. But yeah.
Okay, thank you.
I wanted to talk about a bigger vision that I have called Trustworthy AI. I want to make 2 points with my talk. First, to introduce the notion of trustworthy AI as opposed to robust AI. And it really comes from my experience in the cybersecurity community and the formal methods community. Trustworthy computing has come to mean various properties of trustworthiness, everything from safety to security to privacy to reliability, availability, and usability, and these are of traditional computing systems. For trustworthy AI, I think we need to introduce new properties that AI systems bring to the table and that computing systems in the past have not had to deal with. And these properties include accuracy, obviously, robustness, which is the topic of this workshop, fairness, which I understand people are also addressing at this workshop, accountability, transparency, interpretability, explainability, and ethical issues. As with trustworthy computing, some of these trustworthy properties are not easily formalizable, like usability. And the same will be true for AI systems. So my first point is to promote a new research agenda, which I call Trustworthy AI. AI systems are actually upping the ante in terms of the trustworthiness properties we need to address. The second point I want to make is, where does verification fit in? And obviously, from my background in formal methods, I want to argue that AI systems are amenable in some ways to formal methods more generally, but formal methods techniques as we know them today for traditional computing systems also need to be rethought. I do think a framework for talking about formally specifying and verifying AI systems from the formal methods community still makes sense, where we talk about M, a model of the system satisfying using some logical framework, some property P, like robustness. I think what we need to add to this framework is what I call D in my talk. D stands for the data that is being used to train and test, and also being used in deployment of the model that we're trying to actually verify. And of course, this is where the rub is. D is analogous to the model of an environment that we have used in traditional formal methods for verifying computing systems. So D stands for the model of the data. Okay, am I over a minute?
I'm sorry, Robert. Largely.
Okay.
Do you have one more word to summarize?
No, that's fine.
No? Okay, sorry for interrupting you. It's just that we are lacking of time. I have two questions for you. One is from Juan, which is asking, today machine learning models we can verify are very limited to small ones. Unlike today, modern deep neural networks are becoming increasingly larger. So do you think it makes sense to use verification technique on these very large models?
Yes, I think what is needed is two things. First, techniques like what Guy Katz had described, using abstraction and compressing, if you will, the original to something that is verifiable. But the second is, I do think we need new formal verification approaches. And I think if we think about D as another part of the verification parameter space, then we could possibly use the constraints we put on D and the properties we know of D to help with the verification process.
Perfect. Thank you. The second question is from Giant. So Giant is asking, when you present the data model or environment, isn't it where all the problem is? In an open environment, you need to have a data and an environment model that is close enough to reality, which is potentially very complex. So how can we assess that these models are good enough to reach the trust needed?
Yes,
for
this is really a very important question.
He will be happy with this.
I don't have a general answer, but what I have is experience from the environment modeling work that we've done for decades in traditional formal verification, which has in fact enabled us to scale up the use of formal methods in practice. And it is, of course, a very careful specification of the environment model, as careful, as precise as the specification of the model itself. So I think what I'm challenging the formal methods community to do is to try to do something similar for modeling D. And of course, this will mean stochastic processes, probabilistic modeling, and so on. But I think that's where the interesting challenge is to the formal methods community.
I think we all agree with you on this. So thank you, Janet.
In my presentation, I just gave kind of an overview of Marabou framework for neural network verification. And Marabou implements two main algorithms, the base algorithm being ReLUplex, which was proposed by Guy a couple of years ago, right, which consists of simplex algorithm with lazy splitting, and in a lot of ways it's just SMT style approach to solving this new combination of theories that the SMT community didn't really know how to handle. And the second algorithm is a more math algorithm to, in particular, handle verification of neural network queries in a sort of dynamic and effort-based way. So, yeah, the most of the technical contributions there were talking about the split and conquer algorithm, which is parametric and allows to shape the search in very interesting ways. And if you attend the demo later today, you'll get to see some of those interesting interactions. And overall, yeah, a lot of from solver side, kind of the challenges, obviously scalability, and we just outlined a number of directions that we are looking into in terms of raising the capability of modern technology. Yeah.
Perfect. So regarding the questions, it seems like you're a huge fan, obviously, because it's just question for me, but I think probably people will have questions during the demo session. So my question first is maybe more related to Marabou itself. So I've used the TensorFlow wrapper, but I was wondering if there is any plans to do PyTorch compatible.
Yeah, we don't have any plans in place. I think a lot of the features that end up in Marabou sort of depend on if there is kind of a clear call for we need this, right? You know, there is a repository, just go and make an issue, right? This is what we need, and then we can kind of like see how to meet that need. I fully understand kind of like both this and kind of the following question in a lot of ways. Talk about how do we now basically train the networks that will be amenable to verification, and obviously this is now a completely different setting from the standard formal verification. So we need some kind of like tight loop to combine the techniques, and for that we would also need the tools to support such a connection interface, right?
Okay. Maybe a second question. It was more related to the presentation of Guy earlier. So if I remember correctly, Guy mentioned that his technique to downsample the neural network to reduce it, he built it on top of Marabou, but I guess it's not in Marabou itself. So any plans to add it directly into the library?
So I guess that's more of a question for Guy in the long term, but so I think we would want Marabou to really become a toolbox, right, where we will be able to integrate all these interesting techniques. In a lot of ways, if you look at SMT solvers, they started as very simple procedures, but then over time they just accumulated and grew into essentially almost model checking engines in their own right. So yeah, again, I think this is more going to be driven by kind of like community need and how do we actually, like, there's also engineering details in terms of like how do we actually keep the code stable and stuff like that. So yeah, I have very diplomatic answers to these questions, unfortunately.
Okay, sorry. So yeah, I'm done for your question. I will just finish by congratulating you because I think your tool is really cool, and okay, I'm not really aware of all the divide and conquer strategy you did in Marabou, but it's working really well, so good work. I'm eager to see your demo.
Okay, cool. So in my presentation, I talk about the AutoLIRPA, our automatic verification library for general neural networks and scalable certified defense. So AutoLIRPA basically extends existing linear relaxation-based perturbation analysis algorithms. This includes a large number of existing verifiers like Cron and Deep Poly. So in our previous work, we actually showed that under the same optimization framework, you can rederive all those verification methods. So especially Cron and Deep Poly, actually they are mathematically equivalent. If you run the two verifiers, you actually get the same results up to numerical errors. So the goal of this project is to extend the Cron-like bound propagation analysis on any computation graphs. It works like automatic differentiation. So as a user, you don't need to know all the bound propagation process. You just need to give me the computational graph. So you don't need to worry how the bounds are computed. So the benefits of this framework is that you got this automatic bound derivation capability, and the user no knowledge of the bound propagation process, and it is actually a superset of many previous works on verification or certified defense. For example, for citizens, we have the work from Wong and Quarter and Resnets, and there are some works on verifying or certified defense on different architectures, and our framework can support all of this. And the second benefit is if you treat the computation as treat the neural network as a general computational graph, actually you can treat the data and weights uniformly. So we can also consider perturbations on model weights. This allows us to train a model with flat optimization landscape, which is actually beyond the application of verification, and no existing works can support this. And another benefit is the bounds you got from this automatic library is actually differentiable, and they can compute it efficiently on GPUs thanks to PyTorch. And so this allows us to train large-scale certified defense models. For example, we demonstrate training on ImageNet dataset, and we can get better results and existing IBP-based approach. And we also use this library for complete verification by using AutoLIRPA as a solver for branch and bound. And because we can utilize the power of GPU for rapid bound computation, this can be up to 60 times faster than MIP-based methods on large networks. For example, we can make the verification time from an hour down to 1 minute. Which can be very helpful for verifying large networks. Thank you.
Yes, thank you. I like your conclusion from 1 hour to 1 minute. Yeah, it's a huge improvement. So here is your two questions going directly from Mark. So Mark is first asking, how do you handle layer behavior depending on the full batch norm during training with Leopard?
Yeah, I think that's actually a very good question. Because if we have batch normalization during testing, that's actually not a concern because it's just a fine transformation. During testing, the batch normalization, you just need a constant. It just becomes a constant. But during training, it's actually a little bit tricky. So what we are doing currently is that we first compute like the mean and standard deviation of the batch of data, and we treat the two numbers as constant when doing the bound propagation process. So that's what we are doing during training. That because if we model the correlations between the data using linear relaxations, that's gonna make the things very complicated, and also we don't actually need that during test time. So actually during training, we want to make our training more efficient. So we just still treat the mean and the standard deviation as constant for training.
Okay, perfect. The second question is, how do you compute or refine the neuron-wise bounds during the optimization of alpha for the work in fast and complete? Do you directly optimize for the bounds on the specification or refine the neuron-wise bounds using different optimization targets?
Yeah, that's actually a very good question. So when we use our framework for the complete verification setting, so there the bounds obtained by our library actually has some parameters. To be exactly the parameters are actually the slope of the lower bound of redwood neurons, because we are using linear relaxations. For redwood neurons, the lower bound is flexible, so we can choose any slope between 0 and 1. So actually, when you compute the bounds of the final output layer, the bounds will be a function of those slopes and also all the intermediate layer bounds. But these intermediate layer bounds are also a function of the slopes. So overall, it's going to be a very complicated non-convex function of all the slopes, and we can optimize that slope to maximize the output bounds to make it as tight as possible. Actually, this can achieve better results than just using linear programming. Because if in general, if you use linear programming, you have to fix all the intermediate neuron bounds. And now we can also optimize these bounds to make the intermediate bounds tighter, so make the overall convex relaxation tighter. So actually, you can get sometimes significantly better than just using linear programming. And we can also run this process, this optimization process on GPUs. So it's also very fast. So it doesn't you get both tightness and also speed. So that's why our framework can success in this setting.
Perfect. Thank you, Juan, and eager to use your LIPA library. I was not aware of it because before the workshop, so happy to have.
I have a tutorial session. I have a tutorial session today, so if you're interested, you can go to the tutorial.
Yeah, there is a demo to in this at the end of the session.
Too many choices. Okay, so this is the end of this Q&A session, and thank you.